Hello, everyone, and I know that we're not in the classroom today, but I said I'd record this. I want to make sure I got this recording done for you guys. That's why you guys can always come back and review this. So let's go ahead and take a look at our bond shapes and this concept we're going to talk about called VSEPR theory. Now, for those who've already seen this before, this is our review stuff that we talked about after the quiz. So, drawing our Lewis structures, we'll do a quick thing. So, oxygen has, so look at O2 first. Now, this is a little bit of a kind of a small gotcha situation because there's 7 rules that we have to follow, right? First rule was find our host, find the host. Second rule was place our guest. Guest. Third rule, count the valence electrons. Fourth rule was feed our guest. Fifth rule was leftovers for the host. Sixth rule was check to make sure the host is full. And our last step, if everyone's happy, probably spelled happy wrong, I do apologize, then that means that we are done. So, we had some rules we talked about who our host is. Usually it's one that we only have one of. In a situation where we have 2 of the exact same thing, obviously one of them has to be the host, one of them has to be the guest. So we're going to place our first oxygen here. And so for step 1, find our host. Step 2, place our guest. And we're just going to place them right next to each other because remember there's only 1, 2, 3, 4 places that we can place our guest around our host. Now, we need to count our valence electrons. Oxygen exists in group 16, also known as 6A, so that's 6 plus 6. So that means that we have 12 valence electrons or 12 dots that we're going to place our, excuse me, we're going to place around first our guest and any leftovers goes towards our host. So let's go ahead and place our 8 dots around our guest first. So there's my 8. So that means 8 minus 12. That means I have 4 dots left. So I'm going to add some dots to my host. So I got to check my host. Right now, I see my host only has 6 dots around it. So my host isn't happy. So what does my guest do? They share. And that means that we're going to get a different structure. We're going to see O dot 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 dot, and we'll move this set of lone pairs in between our host and our guest, so that's why they are shared. And just count, make sure 1, 2, 3, 4, 5, 6, 7, 8 for our host. 1, 2, 3, 4, 5, 6, 7, 8 for our guest. Everybody's happy. That means that we're done. So, real simple, real easy. When we look at B, methane, that should be an easy one. That follows our second hint, well, follows both of our hints for when we're finding out our host. The one that we only have one of, and if carbon's there, usually they're the host. We only have 1 carbon, and we have carbon here, so that means that our good host is going to slide there in the middle. And we have 4 hydrogens, so we're going to just place them around our host. Perfect. So now we're going to count our valence electrons. So carbon exists in group 14, also known as 4A, so it has 4. Now hydrogen only has 1 electron, right? But there's 4 of them. So instead of writing 1 plus 1 4 times, I can just do 1 times 4. That gives me 8 dots I'm going to work with for my methane model. So I'm going to put, now the thing is, remember, hydrogen on our periodic table doesn't quite follow the octet rule. It doesn't want 8 electrons around it. If it wants the same amount of electrons as its closest noble gas, that puts it at helium. Helium only has 2, so therefore I'm going to put 2 dots in between each of my hydrogens, just like that. And I'm going to go back, so I need 8 dots. I use all 8 dots. 1, 2, 3, 4, 5, 6, 7, 8. I have my 2 dots around my hydrogen. I have 8 dots, 2 dots around each hydrogen. I have 2 dots around each hydrogen, 8 dots around the carbon. Therefore, everybody's happy, everybody's done. Chlorine, that's chlorine, oh my lord. Nitrogen trichloride, we have 1 N, and we have 3 chlorine atoms. So if we're following our rules from our find our host, the one that we only have 1 of, good news, we only have 1 nitrogen, right? And then we have, so we found our host, now let's place our guess. We're going to put the chlorines around our nitrogen. And remember, it's not exactly important which way they are. I find it easier, there's only 3, to put them on the bottom. But that's just me. You don't have to follow everything step by step. Maybe you want to put your empty space over here on the left-hand side or below or to the right. It doesn't matter. As long as the 3 of them are there, that's what's important, because that's what we're going to use to identify the shape later. That's why the notes that we have is called bond shapes and VSEPR theory. So nitrogen has 5 valence electrons. And then we have chlorine has 7. So 7, there's 3 of them. So we wrap that up. So that means that we have 26 dots that we're going to use for our nitrogen trichloride. Probably pronouncing that incorrectly, but you know, we all make mistakes. So first step is that we feed our guess. So obviously chlorine wants 8 valence electrons around each one of them. So that's what we're going to do. Bup, bup, bup. Bup, 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 bup. Bup, 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 bup. Bup, 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 bup. Alright, so I have 26 dots. So far I've used 8, 16, 24 dots. So what's the next step? Feed leftovers go to the host. Boom, boom. Now we just gotta go make sure the host has, oh, I forgot these over here. Haha. 2, 4, 6, 8. So our host is happy, our guests are happy. If everybody's happy, we're done. So simple walkthrough on that one. Now for our properties for ionic compounds and how they differ from covalent compounds. We should have remembered from the lab that we did that our ionic compounds had the high boiling points and melting points. They're the ones that did not change when you heated them. But our covalent had low. So if you were looking at your samples, so like number 1 and number 4, number 1 was sugar. And those who've ever done any cooking in the kitchen know that sugar melts pretty easy. And then number 6 was actually wax. They were birthday candles. And we've all seen candles melt pretty quickly. Excuse me. Another thing that we saw was that, that the ionic compounds conduct electricity when dissolved. Now, when we were looking at wax and we were looking at the sugar dissolved in the water, but the wax didn't. But even when we use the detector, the electric current detector, we saw that both the sugar and the wax didn't conduct electricity. So those are 2 very easy ones to think of. Excuse me. And that's all we asked for. We asked for 2. And those 2 came directly from the lab that we got done not that long ago. So, check. We're good to keep moving forward. Now, I want to give us a kind of a look into what the future has for us. So, quick look in the future. We are going to be dealing with some what are known as polyatomic atoms. So, polyatomic atoms, they are compounds that kind of act as one thing. So Nitrate NO3 -1. If we're thinking about making bonds, it can only give up one electron. And that's kind of what we're thinking about when we're thinking about our polyatomic structures. You're going to be given a list of around 10 to, I believe it's 10 polyatomic compounds that you are going to be responsible for knowing, especially when we get into Unit 5. So in the lab that we're going to be doing a little bit later on day 2 or day 3, I'm going to give you a chart of all the polyatomic atoms that you're going to be responsible for, and you're going to want to try to put that to memorization. But here, I want to focus on drawing their Lewis structures, because this seems weird. What's going on with that? That just means there's an extra electron in this compound. So when we're doing the Lewis structures of these, they're going to follow the exact same rules as previous Lewis structures that we've done. The ones that we just did, same thing. Same 7 steps. Find your host. Place, number 2 is place guest. 3, count your valence electrons. 4, feed the guest first. 5, leftovers for host. 6, we check on the host, make sure they're full. And 7, if the host is happy, then that means that we are done. So, as you see here, NO3. So obviously N is my host. Place my oxygens around my host. Now, when I'm counting my valence electrons, I'm going to take that 1, I'm going to add that extra electron. Whatever the number is, whether it's a +1, a -1, -2, -3, -4, whatever that minus number is, we're going to add it to our valence electrons. So nitrogen normally has 5, +6, +6, +6, +1. So that's 6, 12, 18, 19, 24. So we have 24 dots that we're working with here. Excuse me. So 24 dots. Obviously, who gets my electrons first? It's going to be the guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Alright, so I fed my guess. I have no leftovers, so I got nothing to go to host, but I gotta check my host. My host ain't happy. He's still hungry. He needs 2 more electrons. So I'm gonna grab one of these lone pairs from one of my oxygens. So we'll just want to steal one here. Put that there, and that's going to give me a new structure of N dot 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 O. 1, 2, 3, 4. And with moving those lone pairs over, take a look at my host. My host is now happy. Everything's good. There's only one more thing I have to do, is I'm going to bracket this unit and put a -1. That's all we have to do. Nothing has changed in what we've done so far, other than the fact that I've added this bracket and the -1 to indicate that it has a -1 charge to the overall molecule. Remember, when we say molecule, we're thinking covalent bonds. So, I want you to try these 2 right here. I'm going to hit the pause button here, and when I unpause it, you'll see the answers. But I want you to give yourself a shot first. So we have hydroxides, we have an oxygen hydrogen with an extra electron, and here we have chlorite. The Cl here, that represents chlorine with 2 oxygens attached to it. So figure out which one's the host, figure out which one excuse me. Excuse me. Which one's the host? Which one's the guest? Now, I will tell you this. When we see an H, our H's are always on the side, meaning that they are always a guest. So I'm going to hit the pause button here. I'm going to let you guys give it a shot, and I will unpause it in a second. Alright, back at it. We see that we have our structure here. We have our, excuse me, 6. So we have our 6 plus 1 plus 1 gives us a total of 6, 7, 8 dots we're using over here. And when we look at chlorite, 7 plus, there's 2 oxygens. Oxygens have 6 valence electrons, so we times that by 2, so writing 6 plus 6. And then it has that 1 there, so plus 1, so, excuse me, 12, 13, 20 dots that we're working with, and we can go ahead and go back and count our dots to check to make sure we have all the dots that we needed. So, once you've done that, let's talk about the shapes. Why are we putting certain things in a line? Why are we putting things one something above or below? And what are those dots, those lone pairs? What are they doing? What's going on there? Well, what we're trying to do is we're trying to visualize the 3D shapes of our molecules. And we're going to find out that this is going to be determined by what's known as VSEPR theory. And VSEPR theory is going to dictate a lot of what our molecules can and cannot do. And what do we call those? We call those the properties. In a second, we're going to talk about different properties in a bit. But when I see a bunch of capital letters, usually they stand for something. So the V stands for valence, S for shell, E electron, P pair, R repulsion theory. Now, you're going to want to write this down. You're going to want to put a star beside it. You're going to put some exclamation points beside it, because you are going to want to know. You're going to want to know what VSEPR stands for. No, I always put the E first. Very important. And what it is, so we're talking about electron pair repulsion. So they're bouncing off each other. So our electrons don't want to be right next to each other. There's a reason why we put them in the 4 spots, right? When we're doing our drawing, there's a reason why our electrons aren't all huddled in one location of my molecule. So let's say oxygen is currently a -2 because normally it has 6, and we have 2 more electrons. So this is a -2 situations. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. That's normally not how we find our electrons. There's a reason why we space them out. It's because, much like if I take 2 negative-sized magnets and try to push them together, they're going to push away from each other. They don't want to be right next to each other. We've seen this before. But I said that it's going to dictate some properties. What properties can we possibly be talking about? There's 4 main ones that we're going to focus on. So we'll just like to spend this a little quick second. So one of the properties, physical properties that we talk about is the taste or smell of a molecule. Could it be poison or medicine? Depending on the shape, depending on the molecule, we're going to find out that small and flat molecules are often carcinogenic, meaning that they cause cancer, and these physical properties can also determine what something's going to mix with. Why is sugar, so C6H12O6 is sugar, and we all know that dissolves in water. But wax is just like C20H40. I could be wrong on the numbers, but they are these very long carbon molecules. Don't dissolve in water. Why is that? What's going on with that? We're going to talk about when we talk about determining what things mix with. But first, I want to start off with taste and smell. So a great example of this is sucrose, which is a natural sweetener. You find that, excuse me, in different foods, such as fruits and stuff like that. But sucralose is a artificial sweetener, and if you like drinking like diet sodas and stuff like that, why is it sweet? It's because of sucralose. Now, looking at the two, they look pretty dang similar. I see one little difference there. OH. We see the ether structure middle there with OH. We have hydroxyl group pointing down. Here we have chloride pointing up, going up instead of going down. And that's going to affect how things taste or how things will get broken down in our body. And we're also going to find out that sucralose, we can add a lot less of sucralose than to regular sugar added sodas, because sucralose is 600 times sweeter than sugar, and it has to do with, though it's similar in shape, the structure of it. It's going to change how we, as the humans drinking it, taste it. When we think of poison or medicine, here's a great example. You may have heard, several drugs where there's methamphetamine in the drug, and sort of kind of technically. So we have two types of methamphetamine. We have L-methamphetamine and D-methamphetamine, also known as R-methamphetamine, R minus methamphetamine, and also known as S plus methamphetamine. Now the R and S's, that has to do with a chiral, so it talks about it's where this nitrogen is is it pointing towards you. That's what this bold triangle represents, is that the nitrogen is actually coming off of the paper towards you, and the dotted one is going behind the molecule. So that could change how that reacts in our brain. So talking about L and D methamphetamine. L is the legal methamphetamine. That's the one that's used in drugs. Sometimes it's in over-the-counter drugs, such as anti-congestions, stuff like that. So, like, you take something for like a runny nose, you maybe get there. If you take a look at the back of the bottle, you may see L methamphetamine or R minus methamphetamine or levomethamphetamine. That is legal. It does not give you any feelings of what the drug gives you, but you can think L for legal and D for drug. And in the state of Virginia, methamphetamine is a Schedule II drug that can land you up to 1 to 10 years prison sentence in the state of Virginia with a nasty fine. So, whether the nitrogen's coming to you or going away from you, just the movement of one going forward, so my hand now coming towards you, or my hand going away from you, changes the effects of that molecule. It's going to change how that molecule interacts with your brain chemistry, just by something coming forward or something going back. It's crazy. Lastly, we said small flat molecules often cause cancer. This structure right here is known as a benzene ring. So benzene pictured here. Now you don't have to know exactly what benzene is, and I wish I got a better one, but each one of these points is a carbon. And the crazy thing is that these double bonds rotate. So normally when we see benzene, so if you ever get into organic chemistry, or maybe if you do like some research on benzene, you may also see benzene written like this, meaning that those bonds are constantly moving. Now the thing is that benzene is a known human carcinogen and has been directly linked to leukemia and other blood cancers. It's incredibly small, it's incredibly flat, It can easily get into places it's not supposed to, and when it does, it causes problems for us. So, important thing to think about. And lastly, we're going to talk about what it's going to mix with. Excuse me. So we're going to understand this in a quick second. Like dissolves like. It's something we're going to see in the next video that I walk through you guys with. Excuse me. But the thing is that we're going to find that polar molecules like to dissolve. So like to dissolve in other polar, I can't spell anymore, polar compounds. So sugar, C6H12O6, will dissolve in water. But if I have something that's nonpolar, like methane, it doesn't. Dissolve in methane. Why is that happening? Because methane, as we're going to talk about in a couple more slides down the road, is a non-polar substance. Water, we're going to see, is a polar substance, and I have a couple rules for you to help you walk through that. So if I'm looking up here, so these two images, these are fats. So we have saturated fats, we have unsaturated fats. So when we find saturated fats, those who are big into, I always think bacon. Whenever you cook bacon, you always get that grease at the end, right? That's just the saturated fats that got cooked out. Now what happens if I let those saturated fats cool back down to room temperature? They're going to harden back up. They're going to become more solid than a liquid, right? And that's because they can tightly get packed against each other because we have these straight lines of these carbon structures. So very simple for these fats to kind of just stack on top of each other. They will stack on top of each other pretty tightly, right? Because they're straight lines. But those who have done any cooking before, you've probably seen unsaturated fats. Those are your vegetable oils. Now, vegetable oil typically comes in more of a liquid form. It's a little syrupy sometimes, depending on what type of vegetable it's coming from, but usually it moves like a liquid. Why? It's because we see these structures here where it bends the molecules in different ways, so it can't stack on top of each other. And the more molecule spreads out, the less solid it is, and the more liquid it is. The closer my molecules are to each other, the more solid something is. If there's more room to it, it becomes a liquid. If there's even more room to it, they become a gas. So that's what we're talking about. So you don't have to memorize saturated, unsaturated fats, or the benzene ring, or which methamphetamine is going to get me put in jail for 10 years, depending on how much I have, because possession is 9/10 of the law. What I want you to focus on are these 4 items. The properties of the molecular shape can determine how an object tastes or how it smells, whether or not it could be a poison or a medicine, that the smaller a compound is, smaller and flatter a compound is, the more likely it could be cancer-causing, and that it can determine what things mix with. If you get these 4 things down, you're going to be just fine. So, I want to give a much better detailed definition of what VSEPR theory is, and that's what we're doing right here. So once again, I have the words written out here: valence shell electron pair repulsion theory. What is this going to predict? It's going to predict that our groups and pairs of electrons around the central atoms repel to get as far away from each other as possible. These distances are so common and so predictable that we actually have bond angles, and it's going to affect how something reacts or not. Groups of electrons repel to maximize the amount of distance and angle between them. We're going to be able to see the theoretical angle between those bonds that we formed for methane, for water, off of that central atom. That's what we're going with this. So this is where we're going to start using some terms that we picked up from geometry. If you haven't taken geometry, does this mean that you're not going to do well here? Absolutely not. It just means that you may or may not have encountered every one of these names for our bond shapes. That's all it is. But we're going to walk you through everything. So if I'm talking about, so our bond shape is our shape that's formed by the electron groups around the central atom. We're going to see two things. We're going to be able to determine a bond shape and also the molecular shape. And if I remember correctly, we're going to talk about this in this slide. Give me one quick second. Let me just pull for a quick second. Let me just check. I think we do. Yeah, we will talk about them here. Perfect. I could remember it was in this one or the next one, so I just wanted to be on the safe side. Okay. So, what we're looking here is, so we have the number of electron groups around a central atom. So we're going to draw these, and when I'm in class with you guys, I'm actually going to, I have a couple of 3D models that we're going to actually take a look at, and we can see how these shapes are in front of us. But right now it's a little hard because I'm just working with a camera and some printed paper, so it's a little bit of a tricky situation, but work with me. I promise you it's going to make a lot more sense when we all get back together. So, number of electron groups around the central atom. So if I have my central atom, let's put A here, and there's one electron group. So there's something, we're going to put X for my electron group. So A is my central atom. X can represent either electrons or another atom. So these are the two things I'm going to use here. So I have my central atom and one thing right beside it. Because this kind of looks like a line, we're going to call this linear, a term I'm pretty sure you've heard before. Now, those who've ever done the bond angle of a flat line, we should know that that is 180 degrees from one point to the next. But if I'm doing two electron groups around a central atom, so X, A, X, because remember, they want to be as far apart from each other as possible. They don't want to be stacked. They don't want to be stacked up next to each other, because the electrons here want to repel those electrons away, and these electrons here want to repel those guys away. So how can they be furthest away from each other? As if they're in a straight line, once again, forming a linear base shape at 180 degrees. Remember, they want to be as far apart from each other, and there's no further apart from something than the absolute opposite side of the central atom as the first one is. So in this case, both bond shapes are going to equal 180 degrees. But now I'm talking about three atoms, three electron groups around my central atom. So I got my central atom, 1x, 2x, 3x. Now, it kind of looks like a triangle. So we're going to call this a... Sorry about that. I just had to go do a quick check to make sure I was spelling it right in my head. So it kind of looks like a triangle, right? 3 points. 1, 2, 3. Perfect. So we may have heard something similar like this in geometry class. It's going to be... Oh, Lord.